Thanks. It's really great to be here. So I'm going to be talking about the arithmetic and geometry of Brill Noether loci. And it's especially great to speak at ants because I can finally get even with my sister, who's a biologist and studies ants in the real world. So now we've both attended ants conferences. All right. So this talk is going to be something of an olive branch and an invitation from outside of traditional computational number theory. But I think that the questions I'm going to bring up are, well, near and dear to my heart, and I think there's a lot of work to be done, especially on the computational side. So I hope that it will be of interest in this audience. So all original content that I'm going to talk about is based on joint work with either Jeff Smith or Eric Larson and Hannah Larson, who you see here. And when I get to those specific things, I'll point out my co-authors. All right, so the basic idea is that to study a curve, which one often wants to do, for instance, you might want to know what its rational points are or something else about its arithmetic, it's often essential to understand this curve explicitly via its maps to various projective spaces. So I'm not saying anything that you don't know. I took some representative papers from the accepted papers from ants this year, and you see here plane quartics, so curves that are embedded in projective space of dimension 2 by a degree 4 map, or low-gonal curves, curves with a low degree map to P1, and most extremely, hyperelliptic curves, curves with a degree 2 map to P1. So it's been helpful in these projects to understand this explicit geometry of the maps to projective space. And in my talk, I am going to zoom out and focus on the loci corresponding to such maps in their own right, and the geometry and arithmetic of those loci. And as an application, we're going to see how this is related to low degree points on curves, which is a problem often studied, especially from the computational point of view. So that's what's coming. Stay tuned. All right. So the general framework is that we're going to work with C, a nice curve. So nice here is a technical term, smooth, projective, and geometrically integral over a field K. I'm making no assumptions on this field right now, but later we're going to assume that K is a number field when we get to the arithmetic part of this talk. And I'm going to use G to denote the genus of the curve, which I am always going to assume is at least 2 unless I explicitly state otherwise. All right, so let's meet our main object. So it's attached to 2 integers, r and d, which are greater than or equal to 0. So the Brill Noether locus attached to these integers, which I call WRD. It's a subvariety of pic D of the curve, the degree D component of the Picard scheme, which is a torsor for pic naught, the Jacobian, a G-dimensional abelian variety. And it's the set of line bundles of degree D, so that's that D there. And the condition on those line bundles is that their space of global sections has dimension at least r plus 1. So that's the R. So just to point that out, what I did there, this little h naught of CL, that's what I used to denote the dimension of the space of global sections of L on C. So, right, so what I've described for you here are the closed points of this loci, of this locus. And so these are what could give rise to degree D maps C to PR. So let me say 2 words about what I mean when I say degree D map of a curve to projective space, because it might be a little confusing. So this map, it's going to be finite to 1 onto some curve in projective space, and I multiply the degree of that finite part and the degree of the curve in projective space, and that's the overall degree. Okay, so this is the object that we're going to study. Let's do a first example that we've already seen is important. So the first example is if my curve is hyperelliptic. Then by some definition of hyperelliptic, it means that there exists a degree 2 map. I've called it F here from my curve to P1. And so let's see how this is related to a WRD. Well, I can take this map and I can pull back the line bundle O of 1 from P1. So then this is now a line bundle on C of degree 2, because the map was of degree 2, and furthermore, its space of global sections has dimension at least 2. And so what this tells me is that this lives inside W12 of the curve. So this Brill Noether locus, W12, is related to whether or not the curve is hyperelliptic. And if you take another definition of hyperelliptic, its rational points correspond to being hyperelliptic in that definition. Okay, so I've just defined for you a subvariety of pic D, and when you meet a subvariety, I think there are some natural geometric questions to ask yourself about this variety. So the first question is when is it non-empty as a scheme? It's the first question you could ask. And so roughly, to sidestep arithmetic issues for the moment, because we're talking about geometry, this says when is C over the algebraic closure presented as a degree at most D curve in PR. Maybe I should say mapping to PR. By what I said about the degree earlier. Okay, and then if this variety is non-empty, so if CK bar does admit such a presentation, then it's natural to ask what its dimension is, which is roughly saying in how many ways is this curve a degree D curve mapping to PR? Or in other words, how canonical is this map? Are these maps? But another way to interpret the question of how many ways this curve is a degree D curve mapping to PR is the next thing, which is this space geometrically irreducible? So if it's positive dimensional, but it's irreducible, then you can deform the different maps you can deform between the different maps. But if it has multiple irreducible components, then there actually is something different between the maps corresponding to the different components. So I want you to think about this irreducibility as roughly saying, are there other discrete invariants for line bundles of degree D with at least R plus 1 global sections. And finally, you might only expect this space to be geometrically irreducible if it's positive dimensional. If it's dimension 0, maybe there's no reason it should be just a single geometric point. And so if it's dimension 0, you can ask, well, how many geometric points are there? What is the length of this zero-dimensional scheme? And that's the final question. So that's sort of the lay of the land geometric questions that you might be interested in. But we're number theorists here, so let's put on our number theory hats and think about some arithmetic questions that are analogs of these geometric questions. So now, some natural arithmetic questions. So instead of non-emptiness as a scheme, you can ask when are the rational points on WRD non-empty? And instead of asking what the dimension of all of WRD is, you can ask what is the dimension. So I want to get an algebraic variety related to the rational points, so I can take the rational points on WRD of the curve, and I can take their Zariski closure, and I can ask what's the dimension of that subvariety of pic D, the smallest subvariety containing the rational points. And then instead of geometric irreducibility, I can ask for irreducibility over the ground field. So even if it's not geometrically irreducible, is it irreducible over the ground field? And same for this enumeration case when it's finite. So I can ask both of these questions over K and not over K bar. Okay, so I'm going to refer back to these questions throughout the talk. In general, they're very hard, but let's do one example where I can actually answer all of these questions for you. So let's do the example of WG minus 1, 2G minus 2 of the curve. Okay, so this 2G minus 2, recall that's the degree. So we're looking at line bundles of degree 2G minus 2. So I'm going to say L is a line bundle of degree 2G minus 2 on the curve, and this index G minus 1, this is saying that H naught of L is at least G. So when you see something like this H naught of L at least G, it's natural to try to see what Riemann-Roch tells us about this. So by Riemann-Roch, H naught of CL is equal to the degree, which is 2G minus 2, plus 1, minus the genus, plus the dimension of the Serre dual space of global sections, so KC tensor L inverse, which rearranging is G minus 1 plus H naught of C KC tensor L inverse. And notice now that because L was a line bundle of degree 2G minus 2, this is a line bundle of degree 0. So the only way that I can bump up the space of global sections by 1 to get something that's at least G is if this line bundle of degree 0 has a section. And that section gives a trivialization, so it needs to be the trivial bundle. So we see from this that L is in our locus WG minus 1, 2G minus 2 of C, if and only if L is isomorphic to the canonical bundle of the curve. So this space is in fact just spec of the ground field. So I can answer all my questions about that. One, it's non-empty. In fact, it has a K point. Two, its dimension is 0. It's canonical. But of course, we knew that. That's why the canonical bundle is canonical. 3, it's irreducible. And it's geometrically irreducible and irreducible. And 4, the number of geometric points is 1. But even though this was a very simple example, as number theorists, we've gotten a lot of mileage out of studying the number theoretic properties of a curve out of its canonical map to projective space. So it's a very useful locus attached to a curve. Okay, so let's do a slightly more complicated example. So let's look at curves that are hyperelliptic first. So if the curve is hyperelliptic, remember this is already a statement about the Brill Noether locus of the curve. It's a statement about W12 of the curve. So I'm going to use F to denote the hyperelliptic map, degree 2 map to P1, and I'm going to use L to denote the pullback of O of 1, as I did before. Then W13, I need now line bundles of 1 degree larger than L with at least 2 global sections. Well, this contains, certainly, the locus of line bundles of the form L twisted up by any point on the curve. Because its space of global sections contains the space of global sections of just L, but now the degree is 1 larger. So in particular, this is dimension at least 1, W13 of the curve. Okay, now let's look at a non-hyperelliptic curve. And so that I can say something concrete, let's look at a non-hyperelliptic curve of genus 4. If I look at a non-hyperelliptic curve of genus 4 and I use the canonical linear series that we encountered in the very first example, then actually it's an embedding because the curve is non-hyperelliptic. And you can show that it's a complete intersection of a quadric and a cubic in P3. So over K bar, this quadric is generically going to be isomorphic to P1 cross P1. And the geometry of the curve embedded in that quadric, because it's a cubic section, the curve embeds as a bidegree 3-3 curve on P1 cross P1, which means that the two projections onto each of the factors, each of the P1 factors, are degree 3. So there are these two degree 3 maps from the curve to P1. And in fact, using Riemann-Roch, as I did earlier, you can show that these are the only degree 3 maps to P1. And so what that tells you is that W13 of the curve is a canonical degree 2 subscheme, finite degree 2 subscheme of pick 3 of the curve. So I want to point out two things here. First of all, it's 0-dimensional, which was in contrast to the case where the curve up here came equipped with this other special Brill Noether property that it was hyperelliptic. So keep that fact that the dimension was different, keep that in mind because it's going to enter again at the end of the talk. And the other reason is that you can actually use this canonical degree 2 subscheme of pick 3 to do some number theory. So this was studied by Hangzhu in his thesis, and he studied when you could use it to get generators of the Mordell-Weil group, when it was torsion, some really interesting, what the height function associated to it, like some very interesting number theory coming out of this Brill Noether locus. So I think that this is sort of illustrative of what I think one can do with this geometry. All right, but in general, answering these 4 questions, these 4 natural questions, is very difficult. But they also make sense in families. So I can define a universal WRD over the moduli of genus G curves, which is now a subvariety of the universal Picard scheme, PICD, of the universal curve, the relative Picard scheme of the universal curve over MG. And so given this, it makes sense to ask a geometric question, which is what can we say about WRD of C when this class of C in MG is general. So I want to emphasize this is geometry, this notion of general. It's saying that I want to make statements about WRD of the curve that hold for all curves C in an open, dense subset of MG. Okay. So this problem is solved by the Brill Noether theorem, which is a really was proved by neither Brill nor Noether, but is proved in a sequence of papers in the 80s, and I think is really some seminal work that has led to a lot of development in the theory of curves. So we're going to assume that C is general in the sense I just told you. Then the non-emptiness question, this was answered by Griffiths and Harris in 1980. So this locus, WRD of C, is non-empty if and only if the following numerical quantity, rho of GRD, the Brill Noether number, which is G minus R plus 1 times G minus D plus R, is greater than or equal to 0. So whether or not this space as a scheme is non-empty is governed purely by this numerical quantity, and this numerical quantity is exactly what you would expect. It's an expected dimension count. So what this is saying is when you expect this to be non-empty, it's non-empty. Okay, so why is that the expected dimension count? It's because it's the expected dimension. So when it's non-empty, the dimension of WRD, well, it's a subvariety of pic D, so it can be at most G-dimensional, but its dimension is the minimum of rho and G. Okay, so the next question was about irreducibility, and you can deduce irreducibility of WRD of C in the case that rho is strictly greater than 0, is positive, from Gieseker's proof of the Gieseker-Petri theorem and Fulton and Lazarsfeld's connectedness theorem. That together combines to prove that WRD of C is irreducible when it's positive dimensional, but actually something even stronger is true. This universal WRD is irreducible even when it's 0-dimensional. So in the case that it's 0-dimensional, it's a generically finite cover of MG, and the statement here is that the monodromy of that cover is transitive, which shows you that it's irreducible. So that was proved in the latest of these papers in 1987 by Isabel and Harris. Okay, and finally, actually what was done first, because it was valid if the dimension was the expected dimension, which you need Griffiths and Harris proof of that to have this, to know that this is valid, but there are enumerative formulas when rho is 0. And these were proved by Kempf and Kleiman-Laxov. So here's just one example to show you that these are some beautiful combinatorial numbers. So when the genus is even, I'm going to write it as 2 times d minus 1. And the reason I'm going to write it like that is this d is then the minimal degree of a map to P1. So it's the gonality of the curve. And so being the gonality, it says that this scheme W1d of the curve is non-empty, and in fact the number of geometric points is the d minus first Catalan number. And this computation does have applications in number theory, understanding this number. All right, so that was our sort of broad survey of the geometry of these varieties and a lot of what's known in the generic case. Let's now turn to arithmetic for the rest of the talk. So now I'm going to specialize to K being a number field, and I'm going to focus on question 2, which is about the dimension of the Zariski closure of the rational points on WRD of the curve. And in fact, I'm just going to focus on the first sort of thing that you could ask, which is whether or not this dimension is 0 or positive. And actually, really, what I'm going to prove, so prove results about when this dimension of the Zariski closure on W0d of the curve is 0. So the first case when R is 0. But because all of these sets nest as you increase R, so the set of line bundles with at least R plus 1 sections, of course they have at least R sections, etc. So proving something about the dimension of the Zariski closure of the rational points here implies results in all of these higher R cases. All right, so I think that this is a very natural motivated question by what I've told you about Brill Noether theory, but maybe you might also come to this question from a different point of view. So let me rephrase it in that other way. So I can rephrase it to be a question about low degree points. Or sporadic points. So the main player here is this set of points of degree at most d on the curve. So I denote this by C sub d. So it's algebraic points on the curve so that the degree of the residue field extension of that point is at most d. So because I said at most d, oh, let me write this one other way. Let me just, this might be just an alternative way to write it. So it's also the union over all extensions, L over K of degree at most d. So these are number fields of the L points on my curve. So I like to write it like this to emphasize that it's not the points over any one fixed number field, it's the points over this infinite collection of number fields. So it's possibly, behaves very interestingly. Okay, so because I said less than or equal to d, these sets nest. So there are the rational points, that's C1, which sit inside the degree at most 2 points, etc. And these all sit inside this huge set of algebraic points on the curve. And so the questions that I'm interested in are how these sets vary with the parameter d. And in particular, since I've assumed that my curve has genus at least 2, by Falting's theorem, the rational points over here are finite. But when I get all the way across to the other side, to the algebraic points, that's infinite. So I think an interesting invariant of higher genus curves is that phase transition point. When do these sets go from being finite sets to being infinite sets? And because I think this is an important invariant, I'm going to give it a name. So I call this the arithmetic degree of irrationality of the curve over the number field k. And it's exactly what I said. It's the smallest of these indexes d, so that the set of degree at most d points is infinite. All right, so I've just introduced a new thing, so let's do some examples. And now here's where I'm not going to assume that the curve is of genus at least 2, just so we can see what happens in these lower genus cases. So if the curve is of genus 0, then over the algebraic closure it's P1, but it might not be P1 over the ground field. You might not have a point, that's not canonical, but the canonical bundle is always canonical. It's defined over the ground field. And the anti-canonical linear system gives me a presentation of this curve in projective space. It gives me one of these non-trivial points in a Brill Noether locus. So C always embeds by the anti-canonical linear system into P2 as a smooth plane conic. So here's my little cartoon of my smooth plane conic. And now the arithmetic degree of irrationality can be computed for this. So there are two possibilities. The first case is that the curve has a rational point, and the second case is that the curve does not have a rational point. So in this first case, that I have a rational point, well, I can project from that point. So here's my point. I can project onto a line which is isomorphic to P1 over the ground field. And this is now a degree 1 map from my curve to P1. So taking the pre-image of any k rational point on P1, I get a k rational point on the conic. So there are infinitely many rational points, and its arithmetic degree of irrationality is 1. But if I don't have a single rational point, then it can't possibly be true that the rational points are infinite. But geometry still comes to the rescue. So in this case, I can't project from a point on the curve, but I can project from a point off of the curve. And now this projection map is of degree 2, because each line intersects the conic in 2 geometric points. So over a rational point in P1, there are going to be, the pre-image looks like 2 geometric points, or a single degree 2 subscheme. So in this case, there are infinitely many degree 2 points in this case. Okay, let's step up the genus by 1 and see what's happening in the genus 1 case. So now these are all torsors under the Jacobian of the curve, which is an elliptic curve. And using the structure of the Vogt-Chatelet group of torsors, you can show that this arithmetic degree of irrationality can be arbitrarily large. It's not bounded as you vary over all genus 1 curves. So that's something a little bit interesting that happens only in that case. But now in the higher genus case, now this is sort of the situation I was in earlier, and I told you, remember, that we always have the canonical linear series. So if we use the canonical linear series, it always gives me a map to P g minus 1 of degree 2g minus 2, and I can use this to now project all the way down to P1 and get a cover of P1 of degree 2g minus 2. And so taking the preimage of a rational point on P1, I get a degree 2g minus 2 point on the curve, so I have infinitely many degree 2g minus 2 points. So this tells me that the arithmetic degree of irrationality is at most 2g minus 2. And then by Falting's famous proof of the Mordell conjecture, it's at least 2. It's always strictly greater than 1. So this is Falting's. But we're all computational people here. We're not satisfied with just seeing something that's strictly greater than 1. So I think it's really interesting to ask, if we know some stuff about the geometry of this curve, perhaps some stuff about its Brill Noether loci, can we actually say what this invariant is? Or can we say something about this invariant? So for the remainder of this talk, that's what we're going to do. All right, so you might ask yourself at this point, what does this have to do with WRD of C, which I think is a very reasonable question. And what it has to do is I can give you an alternative definition of the arithmetic degree of irrationality. It's equivalently the minimal D, such that if I take sim D of C and I take its rational points, it's infinite. And now we can use the Abel-Jacobi map, the Deith-Abel-Jacobi map, from sim D of the curve to pic D of the curve, which takes an effective divisor of degree D, I'll call it big D, to its linear equivalence class, OC of D, the line bundle. And what does it mean for a line bundle in pic D to be in the image of this map? It means that there is some effective divisor that is linearly equivalent to that line, such that O of D is linearly equivalent to that line bundle. In other words, there's a global section of the line bundle. So the image of this is exactly W0D of the curve. So the question about low degree points is very related to the question about the rational points on W0D. Okay, so let me spell that out. So if the arithmetic degree of irrationality is equal to D, then that means that sim D has infinitely many rational points. And therefore, we have one of two things happening. Either the fibers of this Abel-Jacobi map have infinitely many rational points, or the image has infinitely many rational points. So in case 1, what's the fiber? So the fiber over a line bundle OC of D is the effective divisors E that are linearly equivalent to D. In other words, it's the complete linear system of the line bundle OC of D. And so having infinitely many rational points means that C is a degree D cover of P1. You have this non-trivial linear system. Okay, so that was a nice explanation of what happens in case 1. Let's see what happens in case 2. So in case 2, if the image has infinitely many k points, well, the image, as we've said, is W0D of the curve. And so if W0D of the curve has infinitely many k points, because it's a subvariety of a torsor under an abelian variety, we actually do have theorems to understand its rational points. So Falting's proof of the Mordell-Lang conjecture tells us that the rational points on W0 0D of the curve are equal to the rational points on a finite union of translates B of abelian subvarieties of pick naught of the curve. And so these abelian varieties B give us a way of understanding what the Zariski closure of the rational points could be. So if this dimension of the Zariski closure is strictly greater than 0, then there must exist some positive dimensional abelian translate B that's contained in W0D of the curve. So we took this a priori quite hard question about rational points, and now we've reduced it to a geometric question about existence or non-existence of abelian translates inside of W0D of the curve. So let me give you one example where you could get such a non-trivial positive dimensional abelian translate in W0D. If your curve has a degree D map to an elliptic curve, then the map taking the fiber over points of E gives me a map from E to W0D of the curve. Because to every point E, I associate a degree D divisor, which is this, the fiber over that point. Okay, so from possibility 1, we saw that if you had, that the arithmetic degree of irrationality is at most this geometric measure of irrationality of the curve, which is the gonality. So I've already said this, but let me just remind you, this is the minimum degree of a dominant map to P1. But we can see from the example that I just did that this cannot always be sharp, because my curve could fail to have a degree D map to P1, but could have a degree D map to an elliptic curve of positive rank, so a curve that has infinitely many rational points. So in this case, we see that such an elliptic curve is a degree 2 cover of P1. So by composing these two maps, the curve is a degree at most 2D cover of P1. And so in particular, its gonality is at most 2D. And even though this example of being a degree D cover of an elliptic curve is not the only way you can have a positive dimensional abelian subvariety inside of W0D of the curve, these bounds that you would imagine here actually do hold. And that was proved by Abramovich and Harris when they were studying this problem. So this says, you know, these are the extremes. Namely, the arithmetic degree of irrationality is at most the gonality. That was sort of the case 1, and it's always at least the gonality over 2. But a priori, it wasn't clear whether or not every single thing in this range was achievable. It was known by their work from the 90s that this was the landscape, but it wasn't clear that everything was actually achieved. So that was the first thing that Jeff and I proved that I want to tell you about. So this is joint work with Jeff Smith, just got published this year. So for all number fields K, and for all invariants alpha and gamma greater than 0, there exists a nice curve over K whose arithmetic degree of irrationality is my parameter alpha, and whose gonality is my parameter gamma, if and only if it's in these bounds identified by Abramovich and Harris. Gamma over 2 is less than or equal to alpha is less than or equal to gamma. So I want to say that this result is it's constructive. We actually tell you how to find such curves achieving all of these possibilities. And it comes out of our techniques that we developed for computing these invariants on the nose when the curve is exhibited as a positive curve on a surface. Okay, so this is the landscape. This is a description of what these invariants can be in relation to each other. So I want to focus now on the case of equality in this range. So when the arithmetic degree of irrationality is equal to the gonality. And the reason is, this is when you have the strongest number theoretic results, when you have the fewest low degree points allowed by the geometry of maps to P1. So my entire involvement in this subject was inspired by this paper of DeBar and Klassen from 1993, where they give such examples. So the examples are when the curve is a smooth plane curve whose degree is at least 8. So in this case, so plane curves, smooth plane curves here, I just want to emphasize something about Brill Noether theory. So in this case, they completely compute everything. So the arithmetic degree of irrationality is equal to the gonality, which was classically known by Max Noether to be d-1 when the curve has a rational point and d when it doesn't. And these might look kind of familiar because you've already seen it in the case d equals 2 I showed you. So these lowest degree maps to P1 are achieved by projection from either a point on the curve if it has a rational point, or projection from a point off the curve if it doesn't have a rational point. So one of the reasons why I like this theorem is that it tells you this is true for any smooth plane curve. It's not for a general curve or something like that. It's actually every single curve. So from a computational point of view, if you're handed a curve in P2 with no singularities, you automatically know these invariants if the degree is sufficiently large. And let me just emphasize, another reason why I like it is this strong number theoretic statement. So if you're handed one of those curves and you take the points over all number fields of degree bounded by d-2, this very not finitely generated set of possibilities, then those points that are actually on your curve are still finite. So it's a big strengthening of the a priori Falting's bound, which says the rational points are finite. Okay, so something that Jeff and I were wondering about is what's special here about the plane, right? Implicitly, I have a little P2 lying around, and also what's happening with this d at least 8. So the second theorem that we proved hopefully clarifies these two things a little bit. So we replace P2 with any nice surface S over K. And the property of P2 that we need to make the theorems work is that H1 of SOS is 0, the dimension of this coherent cohomology group, which is classically in the theory of surfaces called the irregularity. So the irregularity has to be 0. But concretely, this is the dimension of the Albanese variety. So it says that the Picard group is discrete, that there are no positive dimensional families of line bundles on the surface. So under these assumptions on the surface, if I have an embedding of a nice curve in this surface, and its class is positive, so in algebraic geometry terminology, ample, then we prove the following Brill Noether theory result. So for all indices alpha that are less than or equal to the self-intersection of the curve over 9, the dimension of the Zariski closure of the rational points on W0 alpha of the curve is always 0. So why does this give me examples where the arithmetic degree of irrationality is equal to the gonality, as I claimed? It's because if the curve is sufficiently positive in a very computable sense, then the gonality of the curve is also going to be at most c squared over 9, and therefore the arithmetic degree of irrationality is equal to the gonality. So you get this strong strengthening of Falting's theorem you get finiteness all the way up until the gonality minus 1. Okay, so I'm not going to sketch the proof for you. I just want to show you the circle of ideas that go into the proof, because I'm proving results about W0 alpha of the curve, but I'm going to proceed via WRD of the curve for r greater than 0. And I'm going to play these different Brill Noether loci off of each other. Okay, so by the Mordell-Lang theorem proved by Faltings, we only have to worry about, the only possible Zariski closures we have to worry about are positive dimensional abelian translates inside of W0D of the curve. So suppose that alpha is the smallest integer such that there exists one of these positive dimensional abelian translates inside of W0D of the curve. Then by some work of Abramovich and Harris, you can use the geometry of these W0D in relation to the Picard scheme to show that this other abelian variety, B2, which is non-canonically isomorphic to B, it's simply the image of B cross B under the tensor product map from pic D cross pic D to pic 2D. It a priori lives inside W02D of the curve, but in fact, it lies inside W dim B 2D of the curve. And so you see that by our assumption that B was positive dimensional, we know that this is greater than or equal to 1. So that means that C is presented as a degree at most D map cover of P1. And now we use the embedding of this curve on the surface in relation to this degree D map to P1 to inductively embed this abelian translate B2 inside a different W0F of the curve. And we win by induction if F is strictly less than alpha because we assumed that alpha was minimal. So actually this bound over here that alpha is at most C squared over 9 is what implies that F is strictly less than alpha. So that's where that comes from. And if you unwind this bound, you get the DeBar and Klassen result about D at least 8 in the case of P2, just by unwinding this. Okay, so that's some sort of exploration of the relationship between the arithmetic degree of irrationality and the gonality when they're equal. But I think a lot is still open about the relationship between these two very natural invariants, especially when you fix the genus of the curve. And not much is known outside of the existence results that I've told you. So another way of phrasing this, by what I explained about the relationship with WRD, is the question, what can we say about WRD of C when C is not necessarily general, when the gonality of C is fixed to be some integer, say E, and E might be less than the generic gonality. And in this case, even the geometry is missing. So, so those geometric questions 1 through 4 were not completely answered. So what is known? Well, if I fix C to be a general curve of gonality E, then it was observed in some papers of Copens and Martins from around 2000 that there can exist multiple components of WRD of the curve, which can be of the quote-unquote wrong dimension, so not the expected dimension based on just the Brill Noether number. And we've already seen this. We saw that in the case of a hyperelliptic curve, which was something special about the gonality of the curve. W13 could be positive dimensional, even though for a generic curve it was supposed to be zero dimensional. So that dimension was partially answered in some papers that were published or appeared on the archive in 2017 by Flieger and Jensen-Ranganathan. So they determined the dimension of the largest component of WRD. So this does partially answer questions 1 and 2. It says when it's not empty and what the dimension is, but it's slightly unsatisfying because we can't say what the dimension is of the other components, and we don't really have an explanation for them. So then last year, it was proposed independently by Hannah Larson, my collaborator, and Cook, Powell, and Jensen, that these multiple components are explained by splitting loci. So I told you to think about non-irreducible WRD as saying that there are discrete invariants that we don't yet know, that are missing from the picture. And so they've proposed that the discrete invariants that explain these loci are splitting loci. So if I come equipped with a map from C to P1 of degree E, and I'm looking at some line bundle on the curve, which might be in a WRD of the curve, then I can always push this line bundle forward under this degree E map from C to P1. And because it's degree E, it will be a vector bundle on P1 whose rank is E. And so by the Birkhoff-Grothendieck theorem, it splits as a direct sum of line bundles, which I'll write as O of L1 through O of LE. And this tuple of integers, L1 through LE, which I'll denote vec L, this is a discrete invariant of the line bundle. So why is this a discrete invariant that refines the R and D that we already had? It's because H naught of CL, because the map is affine, is equal to H naught of the push forward of L on P1. And this is just combinatorially computed from this vector of integers L. And so these really do give a refinement of the Brill Noether loci. So let me write them down. We'll call it W vec L of C, which are line bundles in pic D of the curve whose push forward has splitting type O of vec L or some specialization thereof. Okay, so Hannah Larson proved that if this map from the curve to P1, which was of degree E, is general, then the Brill Noether splitting loci, W vec L of C, have the dimension that you would expect for being splitting loci. So even though this dimension is not necessarily the Brill Noether number, it is still the expectation using this information. So I'll call this dimension, this dimension rho prime. So this gives, a refined answer to 1 and 2. But it still was not known whether or not the splitting type was the only remaining discrete invariant. So whether or not these Brill Noether splitting loci were themselves irreducible, or whether there's something else that needed to be thrown into the mixture to really understand all of these maps. So that's what we prove. We give a complete remaining answer to this question of Brill Noether theory for curves of coming with a fixed degree E map to P1 that are general. So these splitting loci are irreducible if the expected dimension is greater than 0. And furthermore, we prove the monodromy statement. So even when even when this rho prime is 0, the universal W vec L is irreducible. And in this case, that rho prime is equal to 0. So when this is just a zero-dimensional scheme, we can describe this number of geometric points. So we give some understanding of this enumeration problem. So let me end by saying here are a bunch of interesting canonical subvarieties of pic D of a curve whose arithmetic have not really been studied. So I think that this is an invitation and a challenge to understand the arithmetic of these refined Brill Noether loci. So with that, let me say thank you and ask for questions.